In this talk, we're going to cover a lot of things. Hopefully it won't be too fast, and hopefully you'll learn something. So the first thing we'll talk about is just cool things about the internet. So like routing, just some background on TCP, DNS, things that make the internet work, but that us as Rails developers might not touch every day. But I think it's good to know something about these things. Then we'll talk about HTTP, what HTTP provides to us for caching, and then how to handle things like cookies. And finally, the bulk of the talk will be around actually doing acceleration with apps. I'll talk a lot about Varnish Cash and some caching strategies for caching dynamic content. So before we begin, I just want to point out that I work at a company called Fastly. We are a content delivery network. And we're all about real time. So whether that's stats, log streaming, or instant purging in 150 milliseconds, we're all about being very fast. And so we are actually built on top of a fork of Varnish Cash. And we allow you to upload something called VCL. It stands for Varnish Config Language. Now, so does anyone in the room know about Varnish Cash? Have you used it, heard of it? Cool. What about VCL, Varnish Config Language? Okay, cool. So Fastly is hiring. If you're interested, come find me after and let's chat. So I'd like to show a couple of these pictures. Fastly, we run our own infrastructure. So we stick tons and tons of SSDs and RAM into all of our cache nodes. Now, I'm going to talk about internet routing in just a moment. So if you find that really interesting, there's a talk by a colleague of mine called Scaling Networks Through Software, and that's from SRECon 2015, just a couple weeks ago. Check that out. So, things about the internet. First thing to know is that the internet is made up of many different autonomous systems. And autonomous systems, that just means that it's a network controlled by a single person or entity. So for example, Comcast has an autonomous system. Level 3, Fastly, we operate our own network, so we have an autonomous system. And the real key thing here with autonomous systems is that there is an ASN, an autonomous system number. And that's just a unique identifier that identifies that network as something distinct from another network. And so these ASNs are actually really critical in internet routing. So there's this thing called the Order Gate Protocol. It's BGP, and this is used to find the best path through the internet from point A to point B. So the way this works is when you connect up a new router to, excuse me, when you connect a new router to various ISPs that you may connect to, typically you only do this when you have more than one. So all of us in the room might be not doing this, like our hosting providers are probably doing this for us. So when you connect a new router, it pulls all of the internet routes from those ISPs. It then analyzes those routes and finds something that's called the shortest AS path. And all that means is the path through the internet that traverses the least amount of these autonomous systems. So once you find that path, you then store the next hop of that path in your routing table. And this is important because there are these things called peering agreements and peering. So peering is when two autonomous systems get together and exchange this routing information. And so with that comes these agreements called peering agreements. And these define how much traffic can be sent through their network, how much it costs, things like that. And these typically happen at physical points called internet exchanges. Hello? Okay. Some of these are very big, doing like hundreds of terabits a second. And so like Amsterdam, AMSI is one of the largest. Now there's also just like a fun tidbit of information. There's this group called Nanog, and this is a gathering of all of the network operators in North America. They come together, form these peering agreements at Nanog. So if you think that nobody actually controls the internet, Nanog totally does because of these routing. Oh, sure. If you ever hear someone tell you that no one controls the internet, people totally do. And so if you go up, like in a Mac, if you want to see a routing table, it's not terribly interesting, but you can do that with like a netstat-nr on a Mac, or on Linux, you can just route. So that's like kind of basic internet routing in a nutshell. So let's just talk about TCP a little bit. And we should all be familiar that to create a new TCP connection, there's this thing called the three-way handshake. And that takes 3 round trips from server to client to initiate a new connection. And the reason we care is because HTTP runs on top of TCP. So if every time that we have to send data to a client, we initialize one of these new connections, it's going to be very slow because it takes 3 round trips from server to client. Now, there's this thing called the TCP window size, and that just controls how much data the server can send to the client at one time. And just one of the optimizations that you can do with TCP, not necessarily that you're going to do as Rails developers, but that you might expect your CDN or your provider to do for you, is something called slow start. And that's just where you iteratively increase the window size so that you can send more data at one time from the server to the client. Now DNS, we use it every day. It's just the human name mapping to an IP address. So DNS has a TTL, that stands for time to live, and that specifies how long you can cache these DNS records. Now, has anyone used dig or heard of a command called dig? Awesome. So dig is really handy. For example, if you do a dig on fastly.com, you'll see that the question that we ask is, hey, fastly.com, give me the A record for this. And A record, that's just the actual IP address. So in this case, it came back with 4 different IPs. I'm not exactly sure why there's 4 here, but some of them might be unicast routes, some of them might be anycast routes, and then a couple of them are probably for redundancy. So if we do another one, we can see that this one has a CNAME, digapi.fastly.com, and we'll see that that is actually a CNAME to global SSL, and that itself is another CNAME to fallback.global. And then finally, fallback.global resolves to 2 different A records. And the reason there's 2 A records here is just for redundancy purposes. If one of those IP addresses fails for some reason, then there's another one there that you can go to. And also notice, there's some 10s, there's some 29s here. Those numbers are the TTL. And these are pretty short TTLs for DNS. And the reason we do this at Fastly is that this is, we update these very often so that we can always determine the closest pop to where the DNS resolver is. So that's just some background on the internet. Now, like, why do we care? You probably don't necessarily care about that stuff, but I just think it's kind of cool. Now, the rest of this talk is about making things fast. And the reason that we care about making things fast is because it takes time to move data around the world, right? So for example, we're here in Atlanta. Say we have some clients that we need to talk to in Sydney, and that's about 10,000 miles. It's a pretty long distance. So just ideal, like at the speed of light, that might take 80 milliseconds for a round trip from here in Atlanta to Sydney, Australia. Now, in reality, that might take a little longer, and it's actually going to take a lot longer. So you can find this out by doing a ping. And so here's one of our cache nodes in Sydney that I pinged. And you'll see that for a round trip, it takes about upwards of 250, 350 milliseconds. And so when you start thinking about that, and if you have to open a new TCP connection to clients out in Sydney every time you're sending them data, that's going to be a very long time, you know? 3 times 300, that's like 900 milliseconds. So your client's already waiting almost a second just so that you can begin to send them information. Little side note, I also did this from airplane Wi-Fi, and that was taking like 700, 800 milliseconds. So like, airplane Wi-Fi is terrible, but we already knew that. And I was curious, like where these packets were actually going, why it was taking so long. And so you just see here that like bounces around the like plane's WAN for a while, and then like finally it resolved down here in Denver, Maybe I was above Denver at the time, I don't really know. But traceroutes, a fun little tool. Now, instead of waiting for that 250, 300 millisecond round trip time, we can do like some cool things and decrease that, right? So here, in this case, Atlanta to Sydney, it's only taking 20, 30 milliseconds. So like, what's going on here? Like, did we just beat the speed of light? Right? Like, if we did, you know, people like Stephen Hawking probably want to know, because they've been working on really hard problems like this for a long time. So did we just beat the speed of light? No, right? And actually, we cheated. So like, my 4th grade teacher that told me cheating never gets anywhere, like, take that. Like, on the internet, cheating gets you lots of places much, much faster. And the way that we cheated was with caching. Right, with caching. So, with that performance round-trip time stuff in mind, let's talk about HTTP and some of the things that HTTP provides us for caching. Cache control. It's HTTP header. We've probably all seen it, use it, love it, know it. I just want to point out a couple directives for the cache control header that you may be less familiar with. And one of these is s-maxage. And so this behaves exactly like maxage, except it only applies to surrogate caches. Surrogate caches here being your CDN. So you can do some cool stuff where you define different caching policies for your browser or for your back-end CDN caches. There's also some pretty new stuff that's interesting, referring to grace mode. So there's these stale while we validate, stale if error directives. And these tell the cache that it's okay to serve stale content while it does something in the background. So like revalidate, the cache is going to go fetch the fresh content in the background while it's still serving stale. Or an error, same type of deal. If the content is stale, it makes a request to origin. Origin comes back with a 500, maybe it's down or something. So this way, the cache will still serve content out to users and not serve those errors, which, in my opinion, is a much better user experience. I'd rather have my users see stale content than errors. Now, the vary HTTP header is another header that can affect caching. Now, a good use of the vary header would be varying on something like accept encoding. And this checks out because accept encoding has a pretty small set of permutations that can be made in a response. So, you know, there's like gzip, deflate, and like non-cached versions. So all of those get cached, but there's not too many permutations. So for example, a bad use of the vary header would be varying on user agent. Please do not do this because there are thousands of different user agents. So if you're trying to cache responses and there's a user agent header in there, then you're really going to just eliminate any benefit that caching might provide you because there's so many different permutations. Now just some clarifying things on cookies. The set cookie header is sent by the server. The cookie header is sent by the client. And in general, proxy caches like CDNs will not cache anything that has a cookie header in it. And intuitively this makes sense, and it should, because generally when we have cookies in responses, that means there's some sort of private data in there that we don't want to cache in a public cache. So now, I want to talk a little bit about Varnish Cash. So Varnish is a HTTP reverse proxy cache. It works just like a reverse proxy would. So it sits between your user and your server, and all the requests flow through that. So generally, when you see these things out in the wild in production, you'll CNAME your top-level domain, like example.com, to the host name of your cache server or load balancer, so that all of those requests to your top-level domain flow through that cache. And just to give you an idea of what this actually looks like, here's the output of a curl to app.fastly. So I'll just point out a couple things here. First is you see this via header. And so all this does is tell you that, okay, this request was actually proxied. And in this case, it was proxied through Varnish. It could be proxied through something else like Squid or any other proxy cache that you might be using. Now some other headers that are interesting are these x-served by, xcache, xcache hits. And so any HTTP header you see that's prefixed by x dash means that it's not an actual official HTTP header. It doesn't exist in the HTTP spec. It basically just means that someone made it up. So in this case, these are kind of actually relevant to us because the x-served by tells us which cache this actually came out of. So here, I'm in Atlanta, it came out of the Atlanta cache. This was also a miss because this request happened to include cookies. And because it was a cache miss, there's no cache hits. Finally, the thing to note is that we are using connection keep alive here. So curl, in this case, did not actually close the TCP connection. It left it open so that we can reuse it and not do that expensive 3 round-trip TCP handshake every time we make a request. So Varnish comes with something called Varnish Config Language, or VCL. And this is just a domain-specific language for interacting with the traffic that comes through your cache. And this VCL is translated to C and then down in bytecode, so it actually has a pretty negligible effect on performance. As opposed to if you were to do something similar with middleware, where that could affect performance, doing that in VCL doesn't do that. So Varnish and VCL run on something called the Varnish state machine. So the way this works is when Varnish processes a request, that request goes through a bunch of different states. And at each point, each one of those different states, VCL allows you to inject logic at that state so that you can do some sort of processing. So for example, here's a couple different states. Rec V is just the first routine that gets called. Deliver is the last routine that called. Fetch gets called after a cache miss, and hit after a cache hit. And then error is an interesting one. You can do kind of interesting things with control flow there. So a quick example. This is pretty straightforward. Say that we want to block all requests to an admin endpoint, and if those requests don't have an authorization header, we're just going to 401 them. So this code right here, DCL rec v. Remember that's the first subroutine that gets executed. So right immediately when this request comes in, we're going to 401 it. This request isn't even going to pass back to our application server. So we don't even need logic there to do that in our application server to do that, since we can do it out here, right? And then remember, think back to those pings. This is the difference. Doing this is the difference between 300 milliseconds and 30 milliseconds, right? Because with Varnish now, if we're just sending these errors from Varnish, those requests never take that other hundreds of milliseconds to go all the way back to our application server. So Varnish has something really interesting also called synthetic responses. And this is just best shown by example. So say we have a page, and this page has a like button with a counter. It counts the number of likes that this video has, or whatever. So typically, how we might cache this is using a traditional reverse proxy would be, maybe there's a piece of JavaScript in the page. When you click that button, it fires off a post request. That post request goes back to your origin server. It does a DB update, and then comes back with a 200. And then when the JavaScript on the page sees that 200, it'll increase that counter. Now again, think if you're going back and forth from here to Sydney, that's going to take a really long time. So what synthetic responses allow you to do is completely bypass making that round trip to origin. So the way that this could work is that JavaScript on the page makes a post. That post gets to your cache, and then you can have a synthetic response with just say it returns 200 OK, and that 200 gets back to the client very quickly, so that the client or the browser in our case gets that feedback immediately, and the user is just not sitting there clicking the button, going hey, what's going on? I'm clicking you, you're not updating. And then the way that you would eventually update the database is you can send a log out from your cache, and you have some background job that's processing those logs in real time, watching for updates, and then actually doing the update. So the way that this actually looks in VCL is pretty straightforward. So we have recv, the first function that gets executed. We're saying if the URL matches like some endpoint and it's a post, we're going to throw an error. And here, we're throwing error 666. Now, that's not a real error, but that's okay. It doesn't matter because what that's going to do is going to break the Varnish state machine. That's going to break out of that and immediately go to this VCL error. Now, VCL, all of these VCL functions are global, and so they operate on all requests. So what we have to do in this error function, or submodule, is check, okay, we say, it's a status 666. If it's 666, we know that this is going to be a synthetic response. So we're going to set the status to 200. We're going to set a content type, and then our actual request body is just okay. And then we deliver it. So that's how you can do this, and potentially this would save you hundreds of milliseconds on that round trip back to origin. And this works well for things that eventual consistency is okay. If you have things that actually need to be consistent, this won't work out for you, right? So let's move on, and with some of that Varnish VCL knowledge in mind, let's talk about strategies for caching dynamic content. Now first, let's talk about what type of dynamic content is actually cacheable. So pure, truly dynamic content isn't cacheable. And that's stuff like real-time statistics, or credit card numbers, things that actually we don't want to cache. But generally, when we think of dynamic content, such, for example, as a JSON API, that's actually pretty static and it's actually pretty cacheable. The only problem with caching it is that it changes unpredictable. So we need some form or some way to be able to invalidate that. Now, there's a lot of different strategies for caching these dynamic types of things. So one of them is short TTLs. There's a thing called edge side includes. You can do AJAX. And then there's API caching with event-driven purges. So the way that short TTLs work is pretty straightforward. Basically, in your cache control, you set your max age to something very small. So for example, you can set it to 1 second. And so what this is going to do is your caches are going to cache this thing for 1 second. All requests that come in will get that cache content. But then basically what you're doing here is flatlining your requests back to origin. Because your origin is only going to see 1 request a second from the cache. And it's going to absorb all the other load. So it's pretty cool. And this is a pretty easy strategy. You don't have to think a whole lot about doing this. And this works out pretty well if your cache doesn't have some sort of invalidation mechanism that's fast enough to keep up with dynamic content. Now, edge side includes. Has anyone heard of edge side includes? They've been around for a really long time. Now, so the way to think about these is kind of like Russian doll caching. The way these work is templates are generated and cached on the actual edge cache, and then for pieces that are actually dynamic, such as personalized user information or things like that, you can actually fetch that content back from origin, get it back, and the template is actually generated at the cache and sent out from there. So the way this actually looks in real life, say we have a nav bar, there's some links in it, and if a user's logged in, we want to be able to show their avatar and maybe their name there to give them a personalized look and feel. So the way this works, you'll see the ESI include. That is a type of keyword here that the cache will look through when it parses your HTML. And then to actually insert the content in there, it's going to make a request back to your application server that might look something like this curl. There'll be a cookie there. It'll be to the path that's defined in your source. And then here, we're returning, okay, the name and an avatar. And so this doesn't just work for HTML. You can do this with any type of content, whether that's JSON, XML, whatever. And you can template these things at will. So those are edge side includes. Now, another way to cache dynamic content and make your applications faster is to extract all of that dynamic content into APIs and then fetch that asynchronously from the client. And this is good because we can get our HTML to the client faster. Maybe we won't spend so much time building it on the application side. Now, when we have these APIs that Ajax is calling into, we can actually cache them. And so we can do this by setting a cache control with some reasonably long TTL. Maybe it's a couple days. We don't really know. We don't really care. Just something that works out for you. And each response will tag with a cache key. Much like in Rails Russian doll caching, you cache with a cache key. Except in this case, we're going to use an HTTP header called surrogate key. But surrogate key really just means cache key. Like, use it like that. And then, so once that content is cached, it's tagged with those surrogate keys. When it changes, we can perform a purge on that surrogate key so that that content is removed from the cache and it gets updated on the next request. And so the way this might look in a Rails app is, in our get methods like index, we can set the surrogate key. Here we're using just a table key from the active record model. And then say we have update that maps to an HTTP put. When this content updates, we can issue the purge and then render the new content. So Fastly, there's a Fastly Rails plugin that exposes some of these helpers to you. So check that out if that's maybe something you are interested in doing. Now, Rails also helps us out because it injects this CFRF meta tag token into all of our layouts. And so this is good, and this is like, we don't want to eliminate this, but we can't cache that base HTML when there's a unique CFRF token in each page. So one of the ways that we can extract that to make it more cacheable, that base content more cacheable, we can use an edge-side include to include that CFRF tag. We could maybe add that CFRF token into the cookie and client side extract that from the cookie somehow. Or my favorite one of these is to extract that CFRF token into a private API endpoint, and then you can Ajax that into the page asynchronously. So we're approaching the end. This is kind of the last strategy I'm going to talk about. And this is caching things when your responses have cookies. So the way that you do this is when a request with a cookie comes in, you strip that cookie out of the request and save it to a temporary variable. Then you'll do a normal cache lookup like you would, and because you stripped that cookie out, that won't be part of the cache lookup. And then once you fetch that content from the cache, you can set that cookie back on the response from the temporary variable. Now the way that this might look in VCL is something like this. Here we have recv. Remember, it's the first submodule that's a subroutine that's executed when a request comes into Varnish. So here we can say, if there's a cookie named this cookie that I'm looking for, take that cookie, store it in a temporary variable, and unset the cookie header. And then similarly, VCL deliver. This is the last subroutine that executes before you deliver your content out to your client. Here we can say, if we set this temp cookie, set the set cookie header to the value of that cookie that we temporarily stored. And so this is how it works when there's a cache hit. If there's a cache miss, it's slightly different because you will have to fetch that content from origin. But you can do that. VCL fetch is the subroutine that executes right after the response comes back from your backend application server. So here what we're saying is, if there's a set cookie header in that response, store it to this temp variable, rip it out of the response from your application server so that the cache can actually cache that. And then back here, when we deliver, we'll just go ahead and set it again. And so that's how you can cache content that has cookies in it. You basically fake it. And so that's about all. I'm pretty much done here. So just final thoughts. Tools like dig and traceroute are super helpful to debug network problems. Tune your cache control headers. You can get very, very fine-grained control from your cache by using this. And then I didn't really touch on this too much, but try replacing some of your middleware with logic and VCL at the edge and see what happens to performance. Finally, we talked about a couple different caching strategies. None of them are wrong. They're all right. But pick one that is most comfortable to you and you think will be easiest for you. And finally, we talked about stripping cookies out to cache what would otherwise be considered private content and uncacheable. So that's about all that I have. I think we have some time for questions, if anyone has any. Yes?
Is Varnish something that would replace my existing reverse proxy that
So the question is Varnish something that would replace your existing reverse proxy like Nginx? And the answer is, it doesn't have to. So you could totally put Varnish behind or in front of Nginx, like however you want to do it. And I mentioned that like those via headers, if you have two reverse proxies, it's just going to append each proxy that goes through into that header. So you'll be able to determine that. It could, absolutely, sure. Any other questions? All right. Oh, in the back.
For the synthesized responses, is there a way to handle errors?
Sure. So the question is, in these synthetic responses, is there a way to handle errors there if you get one from your origin server?
Yes.
And the answer is yes. I didn't cover it because it's a little bit more of an advanced topic, but absolutely. You can define some logic there that says, if I get a 500 back, do this instead. So absolutely.
Thank you.
Any more? Yeah.
Are there any significant amounts of the internet that don't respect these cache timeouts?
The question is there any significant part of the internet that doesn't respect these cache TTLs? And the answer is probably not, unless you're using a really terrible cache. In general, as long as the person who implemented your cache was reasonably sane, they should be able to handle these TTLs. Yes?
A lot of ISPs, thinking from the point of view of the end user, a lot of ISPs implement sorts of edge caches also. How do they play well together? Do they talk special header language between themselves? So that if an edge cache closest to the user, how would it know to expire sooner than its default time?
Right, okay, so the question is, various ISPs may have their own edge caches, so how can you guarantee invalidation of that content? Is that along the correct lines?
Yeah, let's say you have an edge cache really close to you, so the first thing you're going to hit, and it has a ridiculously long TTL. I'm
Sure.
not pointing fingers, but let's say,
a year.
AOL has, ridiculously long edge cache times. And then somebody goes from that cache to your cache.
Sure. Okay,
And you're
so.
popping. So you're likely to be warm in the localist cache.
Sure, so I'm a little confused by your question.
I'm just trying to tease out whether there's any way that the two caches are talking to each other so that you end up with what's realistically recent content.
Right, so I mean, if you invalidate a piece of content on your cache and there's another cache sitting behind that,
I'm thinking
that's
ahead of it.
or ahead of it. Right, so if there's something cached in front of the cache that you actually own, then you really don't have any control over that. And it's not, like, you can't even say that maybe they support purging or invalidation. don't even know. So really, the only thing that you know about is a cache that you control. I hope that answers your question.
It does.
Sorry.
It's not what I wanted to hear, but it's fine.
Right. Yes.
For the synthetic request, just replaying the request sort of like a background.
The question is, for the synthetic requests, does it just replay that for the background job?
Right, does it like queue them up and send it to Oracle?
Okay. No, so my example actually, where I was doing this, I totally left out the log statement, so I apologize for that. But there's a VCL subroutine called VCL log, and so then in that, you can check for those error codes, and that's where you can define how your log looks and where it gets sent out. But that happens in the flow of the processing that request response. It's not queued up or anything. It's immediately sent out in real time to wherever you want it to go. Last one, I think.
For example, like short TTLs, does that have much slowing down the time and they do a lot of DNS?
Good question. So the question was, with short TTLs, does that end up slowing down the client since I have to do more DNS lookups to fetch the content? And the answer is not necessarily, because if you could define something in that cache control, you can define a directive that specifies for it to be okay for it to be stale. And so that way, you don't have your clients necessarily requesting this content every second or every time. So you could put like some grace window on there, maybe 30 seconds, 1 minute, if your content allows for that. And I think that's about all we have time for. If you have more questions, feel free to come and chat with me.